want to talk a little bit about this little Stringybark Creek project. And in a past one of these seminars, I talked about its role in flood mitigation, and there was a presentation yesterday by Stephanie Amel talking about maintenance, etc. So today I specifically want to focus on the water supply aspects of this project. This is a project that has as its central aim to test the question about whether the water quality, the hydrology, and the ecological health of a waterway can be restored by essentially retrofitting the stormwater system using the type of technologies we're familiar with and other presenters have talked about, so rain gardens and rainwater harvesting, etc. But today I'll focus much more on talking about, well, what have been the water supply behaviours and performance of the system. So it's a very large project, been running essentially since 2008. Many people from across the University of Melbourne, Monash University, Melbourne Water, and many other partners. And I particularly want to acknowledge Chris Walsh, who I kind of see as the spiritual leader of this project. So nothing exciting in telling you that urban stormwater runoff degrades streams, and so I'm on to slide, I think it's slide 3, the slide where it just says urban stormwater runoff degrades streams, and there's 2 photos. So a picture of a street and then a picture of a stream. So you might wonder why I'd waste time telling you something you know so well. But it's a really important point, I think, to make, that the typical approach that waterway management agencies have had to dealing with degraded urban streams has been to go in and intervene in the stream. So place rock in the stream or try to recreate habitat diversity in the stream, etc. And studies all around the world by people like Emily Bernhardt and many others show that essentially you get no ecological response from doing that. So there's been many studies and meta-studies showing exactly the same thing. And so our hypothesis in this question is, so on to the next slide, we hypothesize that if you want to restore those streams, if you want to, when I say restore, improve their health, then you need to make the stream flow, so the flow regime, the water quality, much more like that of a natural catchment, and that gives you the best chance of that stream then having an ecology which is I suppose desirable or healthy. So we hypothesize that we therefore need to reduce the size and the frequency of untreated runoff going into the streams. We need to restore the quality and pattern of that flow regime, and that flow has to be of an appropriate quality as well. And to do that, we really need to get the runoff volume to match the pre-developed volume. So I'm still on that slide with the tank and the rain garden. And that point about volume is really important, because it essentially is saying there is an environmental imperative to remove that water from the stream, and that creates therefore a very big opportunity, as we know. So our test catchment is the Little Stringybark Creek catchment in Mount and I'll move to the next slide, which has an aerial photograph showing the catchment. So catchment's about 13% total imperviousness, around 9% connected impervious, so there's some informal areas. And so it's a fairly typical outer urban kind of catchment with lots of residential suburbs, sort of lots of residential allotments ranging from sort of 400, 500 square metre allotments up to much bigger ones in some of the areas. It's got a bit of commercial, so there's a picture here of a gas station, and also some industrial, so last photo on this slide. is one of the little industrial estates where you've got lots of things like a concrete batching plant and some panel beating car repair industries and some recycling centres and that sort of thing. So on to the next slide, which is titled 300 Stormwater Retention Systems. So between late 2008, early 2009, and now we've constructed some 300 stormwater retention systems. We'll use that term as a general term. These range in scale from many at the individual household scale, so the allotment scale, through a sort of middle scale of 1,000 to 5,000 square metre catchments. So these tend to be in large systems next to the streetscape, or in the case of the gas station, we've got a very large harvesting system there. We're harvesting some 2 million litres a year from that catchment and using that for a car wash facility. And then through to some very large systems where we are harvesting water from quite large impervious catchments and then supplying regional sports grounds. So on the right-hand side you see some 800,000 litres of storage in those three large tanks. And those have a filtration system, UV system, and then application to the sports facilities you see in the top right. So on to the next slide, which is titled How Well Do the Systems Work? So I just want to talk a little bit about how well they're working from a water supply point of view and how that interacts with their primary, our primary goal of mitigating the stormwater impact. And I'll talk a little bit about their operation, the maintenance and the risk, a little bit about the energy use monitoring we've been doing, and a little bit about their costing performance. So just reiterating this point that in this catchment, so this slide comes from Perrine Hamel, in this catchment, as is the case in any urban catchment, essentially we're dealing with a very large excess of water, and so our whole approach is to try to get rid of that excess and then the remaining water to filter using the type of technologies that Kufang and Dave and Meg have all been talking about. So in this case we've got about 85% of the rainfall which we have as a resource, because that's the excess rainfall that we're excess runoff that we're trying to deal with. So that slide's entitled Volume to Lose, Volume to Use. So I'll click on to the next slide, which is entitled Performance of Household Rainwater Tanks. And so there's a table here which just shows of the some 300 systems we've installed. We've been monitoring quite intensively 12 rainwater tanks, and this is work we did. This was done by Matt Burns, a postdoc in our team, and a PhD student, and so he did this as part of the CRC Water Sensitive Cities project on stream ecology. So he monitored these 12 rainwater tanks, looking at their performance in terms of water supply, but also their simultaneous performance in terms of runoff retention. So we've got this dual goal, of course, of reducing discharge to the stream at the same time as supplying water. And again, that might seem obvious to you, but there's some optimization to play with here to make sure we get the best outcome for both of those, and I'll talk about that in a minute. So on to the next slide, which is titled Tank Water versus Mains Water, and this gives a percentage in the dark grey, percentage of the average daily water use that's coming from the tanks, and then the percentage that's being supplied by mains. So the supplier here is Yarra Valley Water, and we have access to the mains water use from each house, and this essentially allows us to see, you know, which houses are using a very large proportion of rainwater for their total needs. So if we have a look, for example, at the household 1, we can pretty much assume that they are using their rainwater harvesting only for outdoor uses, and it would even suggest that their system has failed at some time because there's a very low proportion being used, supplied by rainwater. Whereas if we look at something like household 8, then a very significant proportion is, I'll just turn off my phone, a very significant proportion is rainwater. If we look at household 9, household 9 is using the rainwater for everything. So in fact, they don't bring in any mains water anymore. So they have a full treatment system on their supply, and they use our rainwater harvesting for everything. So on to the next slide. So if we think about those households, we see that quite a few of them are not using rainwater for a large proportion of their use. And so if we then look at our monitoring data in terms of the level in those tanks, we see that a lot of those tanks are overflowing quite often. So in other words, when there's a rainfall event, essentially they're discharging to the stormwater system the same as if they weren't there. So that's obviously not a desirable outcome from the stormwater mitigation point of view. So we have been working to develop a kind of hybrid system where the rainwater tank might have an outlet, you know, halfway up or 3/4 of the way up, that supplies passive irrigation to a garden area just through a drip line, essentially, or it might do that through a second tank. So there's various ways of doing it. But essentially what we're then doing is dedicating a proportion of the tank to passive irrigation of open space, whilst the lower part of the tank is dedicated to the what I'll call active uses of that water. So that's a way of improving the runoff retention performance of the systems without any energy costs, etc. These are just passive, so draining under gravity. The question, of course, is, in doing that, do we reduce the reliability of supply of the tank by a significant amount, such that the user of that tank, you know, perceives that it's less attractive to them? And to answer that question, so I'm on to the next slide, which is called Big Impact on Retention Performance. And on that slide, you'll see essentially a cumulative frequency distribution, which is the percentage of time when a given level of retention capacity is delivered by the tank. So I'm just clicking the first animation that shows, for example, in the case of a tank here that supplies toilet and laundry, by adding the passive irrigation, which we call leak here, we probably could have come up with a better marketing term, we increase the median retention performance from about 10 millimeters to about 18 millimeters. So what does this mean? It means that 50% of the time that tank is able to now retain the first 18 millimeters of rainfall before there's any overflow. That's a fairly significant event, so not many rainfall events would be greater than 18 millimeters. And then that passive irrigation essentially drains back down over a period of 2 or 3 days. So from a runoff retention performance point of view, that's giving us a significant improvement. It's getting up to the sort of target numbers we would be wanting. So the question is, how much is that affecting the reliability of supply? So I'll click on the next slide, which is titled no real impact on yield. And so here we see a similar type of plot, but in this case the y-axis is percentage of demand supplied, and you'll see that in the two cases, so toilet plus laundry or toilet plus laundry plus hot water, in each case where we add this passive irrigation, which we call a leak, you'll see that it has a very, very small change on the reliability of supply. So in other words, we find that we can optimize the system to maximize the runoff retention performance with very little impact on the user's benefit received in terms of the amount of water and their reliability of water. Remembering, of course, that all of these systems have automatic switch over to mains, so they don't notice necessarily that the tank is not supplying water, but still the aim is to minimize their potable water use, so that's why the optimization occurs. All right, on to the next slide, which is called decentralisation of risk. So one point to make is that we're doing quite a lot of investigation in terms of the reliability of these systems, and we find that these rainwater tanks, where they're operated by a householder, have a non-negligible failure rate, so something around 20% seems to be common, that in any one time there's 20% that might be partially or completely malfunctioning. So for example, pump might have stopped working, or the switchover might have stopped working, or the inlet to the tank might be blocked, or various things. And we've actually been working with the retail water authorities on some kind of new business models that would see rainwater tanks actually installed, supplied and operated by retail water authorities. So the retail water authorities becomes a provider of not just selling water through pipe systems, but they supply water services, including tanks. And that way, when you structure the model that way, you have a much more guaranteed level of maintenance, because you have a regular maintenance. When the meter reader comes to read the meter, they also check the tank, etc. So several times a year the tanks are checked, and telemetry systems make this a bit easier. In terms of at the other end of the scale, the more centralized systems, there's obviously normally a lower risk of failure, because there's more disciplined maintenance regime in place. Having said that, that's not always the case, and we see cases where the risk of failure might even be higher, because the institutional capacity to maintain these systems isn't always there. But the other point is that these large systems, the impact of the failure is greater. So some interesting trade-offs to play with there. All right, on to the next slide, called energy use comparisons. So one of the questions we asked ourselves is, how much energy are these household rainwater harvesting systems using compared to, for example, the potable water system? And if we look at this table, or look at the, actually probably best to look at the graph down the bottom, so you'll see that Melbourne's potable water system before desalination was put in place has a very, very low energy intensity. It's one of the lowest in the world, so somewhere around 0.11 kilowatt hours per kiloliter, so really impressively low. A gift of our topography, I suppose. We're sitting supplied by surface water coming from the uplands. However, the production, obviously, of water using desalination is a completely different game, and so we're into much, much higher energy use. And in fact, this plot shows the annual carbon dioxide emissions rather than the energy use, but of course they're directly related. If we look at the rainwater tank systems, there's two things we notice. The first is it sits somewhere in the middle. So it's significantly higher than the gravity-fed reservoir system of Melbourne, but it is significantly lower than the Melbourne desalination cost. And I should say the desalination cost is just the cost of the energy cost of desalinating the water, not the cost of transporting that water up from the lowest point in the landscape. So in fact that number is very conservative, and it's likely to be significantly higher. But we do notice that in the rainwater tank systems there's significant opportunity to influence the energy use intensity by the choice of pump systems, and we have done a lot of work on measuring the performance of different pump systems under different use patterns, etc. And for example, so we see a number there of kind of approaching 375 300 and somewhere close to 400 kilograms of carbon dioxide there, but that can be reduced by more than 50% just by the specification of efficient pumps. All right, next couple of slides. So I'll skip through the slide called costing. I just want to make the point here. So on the next slide, it's a graph showing the impervious area treated and the cost treated. So dollars, so thousands of dollars per 100 square meters. So just want to make the point that the sort of mean cost is around $1,500 per square meter, per 100 square meters. We've got some projects that actually cost less than zero because the value of water returned by them is greater than the cost. 2 points to make. First of all, the natural instinct all of us would have would be that there would be some economy of scale, so we'd see the cost significantly reduce with bigger systems, and that's not what we see in reality because of the bigger contingencies and bigger sort of setup costs of big projects. So I'm often surprised how often I hear at conferences, you know, economy of scale, and fair enough to say it if you've got empirical data, but in most cases, people are just sort of assuming that's how it is. The empirical data we've collected suggests that that's not the case. One thing I will point out here is that these costs are all for retrofits, so these are retrofits of existing households. We've done some costing on greenfields, and of course you get very different numbers. You get numbers shifted down substantially so that the life cycle cost over even 10 or 15 years is in most cases going to be negative. All right, on to the next slide, which is a quick life cycle cost analysis. So if we take a mean cost of $1,600 per 100 square meters, so that's a $4,000 cost for a 250 square meter roof, which is average there. At a 30-year life cycle with a 5.5% discount rate, which is pretty typical for Australia in this current decade, that is about $240 a year per household. This is based on 2011 costs of water when we did this analysis. That life cycle cost essentially ends up zero if the water price doubles, and we are a fair bit of the way there already, so we're kind of getting close to that point already in 4 years. The other point to make, I suppose, is if we think about that as a cost of dealing with stormwater, so $240 a year, the mean wastewater charge in Melbourne is some $500 a year, so it actually makes dealing with stormwater look like a fairly cheap thing, and that is partly because of the water supply benefits that are accruing. Okay, next slide on to conclusions. So just to make the obvious point that we see a nice synergy here between the waterway health benefits and the water supply benefits. The energy use of these rainwater harvesting systems is significantly greater than gravity, obviously, but very substantially less than desalinated water. costs around 50% of wastewater disposal cost, which is attractive, but with the increases in water costs that have already occurred and are forecast to occur in the next 5 years, we essentially see these systems ending up with a negative life cycle cost. So in other words, a benefit over sort of 20 years. In the case of greenfields, we see that over much shorter time frames, where we see payback over around 8 years, depending, of course, on the context. Okay, and I'll leave it there. Thanks a lot.
Thank you, Tim. That was absolutely fabulous. I think we may need to mute somebody because I'm getting a serious echo. Maybe this will help. So I wanted to lead off with just a quick question, Tim. I was thinking about system-level risks. You know, and your talk really leads nicely into that. Like, for example, one of the unintended consequences or issues that is being faced in Southern California as water conservation begins to happen is that wastewater flows are much lower than they were designed for, and that is creating a situation where some of the wastewater treatment plants are looking at some real engineering challenges, even moving the waste, and you know, issues with odor and you know, just functioning of their systems. Do you see? I mean, you know, you had a case where one of the households went to 100% rainwater. You know, and obviously some of that is going to go to the wastewater treatment plant. But do you sort of see in this experiment some sort of surprises in terms of the system level functioning of the overall water flow through Little Stringybark Creek?
Okay, yeah, thanks, Stan. Yeah, that's a good question. So perhaps specifically in relation to that that wastewater risk, we've actually been working with the Retail Water Authority, Yarra Valley Water, quite a lot, and we've been quite pleased with their encouragement and support for the project. And in part, of course, what we are doing is encouraging people to still use water as they need, so not to necessarily, you know, be pushing water conservation very hard, because there is a great amount of water available. So rather than using less water, we're saying use different water, use this rainwater that's available to you. So in terms of wastewater discharge, the households in this catchment are probably not seeing the reductions that might occur in other areas, because we're instead providing them with this additional resource. But in more general terms, that system level risk question is a really important one, and we have a new Ph.D. student who's trying to understand this question about how do you manage the risk at different scales in terms of maintenance, etc. And I think there really is some good work to be done in new business models that address this. So as I say, in this retrofit context, we went in and we've put rainwater tanks in on individual allotments, and then the landholders become responsible for them. In the ideal world, that's probably not the model I would use. I would have rainwater tanks be supplied by a supplier like a water authority, or I'm going to call them a water services authority, who then you know, monitors them using telemetry, etc., so they can tell when a tank fails, because you know, the telemetry is saying, hang on, it rained 10 mil, but the water level in the tank didn't change. There's something not right here, so it sends out a little alarm saying you need to go and inspect that one. And it could be a hybrid where it sends a little text message to the householder saying it looks like your tank is blocked. So I really think some of these system level risks and how we deal with them is an area ripe for some applied research. And I think particularly some of the cheap sensor technologies and communication technologies that now exist really place us in a position where a lot of those kind of barriers are easy to solve. I know Dave, for example, Dave McCarthy's been doing a lot of work with those Arduino sensors, and those sort of things become the very cheap basis of a solution to a lot of these problems.
Thank you, Tim. Just as a kind of follow-up to maybe make my question a little more intelligent, because I realized that you weren't really encouraging conservation here in retrospect. You know, it does seem like it poses a risk to the business model for the water suppliers. I mean, if this really does take off, and you kind of hinted at an alternative business model, which is that the water suppliers essentially shift their focus from centralized supply to decentralized supply. Can you comment on that a little bit?
Yeah, that's a good point. So it's a risk in two ways. It's a risk in a direct way in that, all right, they're going to sell less water. It's also a risk in Victoria because of, or in fact most of Australia, because of the structure of the way wastewater is charged, and that is that you pay for you pay your wastewater discharge cost essentially as an estimated proportion of what your water use. So it's assumed that, for example, 70% of your water use must be discharged to wastewater, and so therefore you pay according to that. That's a problem, because if you start using rainwater and all of a sudden your water use drops, then your wastewater charge also drops, even though you might be discharging just as much. So that's a problem. But you're right, we see that for a range of reasons it would be good to explore alternative models where water, I'm going to call them water supply authorities, become water service authorities. Now, a good example is in the power industry, electricity industry. You all of a sudden see some of the big electricity suppliers in Australia saying, if we don't get onto this solar panel and battery technology, it's just going to take over us. So you now see them offering, we will essentially sell you a solar panel and battery system that will allow you to use less of our power, and basically we'll give it to you for free, in fact, and then you can pay us back over 10 years, and we'll maintain it, etc. So they're recognizing that either the market is going to wipe them out, or they're going to evolve into the new market. And we think the same opportunity exists for water authorities to become a supplier of services that source all types of water rather than just supplying the normal potable.
That's fabulous. So I noticed we have lost quite a few of our panel because it's run a bit late. If can you stay for a few more minutes? Can I just cover you with questions? And I think Brandon at least is on the line as well. So, so we'll have a nice private so we'll have a nice private dialogue. We saved the best for last, right? And actually, it's kind of cool because you have that systems level perspective that I think that most of us. I mean, there's very few people in the world who would have that systems level perspective. And so I'm just kind of curious to get your response when you see these talks, looking at the microbial risk and the QMRA and the pesticides, and the degree to which biofilters, for example, remove pesticides. Energy consumption and accusations that have been leveled in the past, certainly that the these LID approaches are very energy intensive, and even ecological risk. We heard Andrew Marion sort of talk about, like, for example, we start going toward ornamentals. Does that pose a risk to invasives and so forth? You sort of surveyed, the really big picture. What do you see as the dominant issues that keep you up at night?
Yeah, it's a really good question. I mean, the first thing is, I suppose we work across some of the big picture stuff, but also in the little, I'll call it the little picture. I'm not sure if that's a good term, but I think it's really important that these kind of details are being resolved, because they're the sticking points. They're the ones that when you go, it's all right when we're talking to the already convinced, the already converted, but when we go and talk to, you know, groups who are kind of, you know, perhaps a bit stuck in the traditional ways, let's say, if we don't have each piece of the jigsaw worked out, so if we haven't thought about the microbial risk, if we haven't thought about the risk in terms of biological diversity in the city, etc., then they're the things that are going to catch us out. So I think it's really important. In terms of the big picture, I suppose I really do see that we do have to get the business models right, because I see, for example, I suppose I'm really excited to see the transition in the energy industry, because at least in Australia I see it's a real dinosaur industry relying on our cheap coal, not wanting to change because the cheap coal is so profitable, and yet all of a sudden the new market comes along and basically says, well, either you change or we're just going to wipe you out and change it for you. And so you now start to see them changing. And I kind of feel like if we can't create that situation in water, we're always going to have troubles. If there's a monopolistic business model that relies on the traditional sourcing of water, and there isn't the opportunity for competitors to that, I think we're always going to be relying on kind of goodwill and you know, getting government to push environmental outcomes, and I don't reckon that's the ideal way. I think we have to have there be a market. So I suppose in the end, the economic stuff really is probably the thing I wake up most about, but I kind of feel like all of that can only successfully happen if all the detail is getting filled in the way that the presentations we've just seen are.
Great. And from a regulatory perspective, do you have worries? I mean, I know certainly in the U.S. the issue, or Southern California, I should say, the issue of cross connections looms large. So
Yeah.
when you start bringing water into individual homes, you know, that's a big concern. And there may just be, you know, a rule out there or a way of doing business in the regulatory environment that basically blocks innovation in this area. So you mentioned business model. Do you think in Australia you have maybe more openness in terms of regulatory change, or is that still is that an issue there as well?
No, it's absolutely still an issue, and you've seen in say southeastern Australia attempts to change the regulatory environment sort of gently, and they've tended to be blocked by vested interests, I suppose. And then you've seen attempts to change it more aggressively, and those have created you know, created more enemies than friends, and so even those who might have agreed have tended to become enemies because of the style of. And so I think we still have a lot of significant regulatory barriers, and I know, you know, there are many groups, so I certainly try to contribute to resolving those, and I know people like Anna and Dave are contributing significantly to those. But no, I reckon there's a long way to go there, and I suppose that's also why I you know, maybe why I feel so importantly about the market, because I tend to think that changing regulation will be difficult if there are significant players who are against it, whereas if, you know, those who care about the environment and those who can see themselves making money out of this all are pushing for that regulatory change, then it becomes harder for governments to resist. So I think, yeah, they have to go hand in hand, but yeah, definitely I think we do still have a lot of regulatory barriers, and the ones you just cited are absolutely the same ones going on here. I was in a meeting yesterday where they were just talking about using swales to distribute water through the landscape in the school, and the kind of state, government people were saying, oh, we don't know about this. We've never heard of this idea of swales. Some decades after they became sort of standard practice, and hundreds of years after they were invented by the Romans. Well, thousands of years, sorry. And they're saying, oh no, that children will drown, etc. And so the people who designed them said, no, we've calculated the maximum velocities, etc. And these are the standards. And then the state government says, well, how do we know, whether those velocities are true or not? And at that point, I was sort of there as an independent expert, and so I said to them, you realise that the formula, in fact, used to calculate that velocity in the swale is the same formula used to calculate the velocity in the pipe, and you said you'd be perfectly happy if it was a pipe. And it really struck me that there's still, even in government, and this is the Department of Education, you'd think they'd be sort of wanting new and innovative. There's still a lot of resistance. So no, I reckon we as researchers need to keep contributing to that and keep, helping to create confidence that, hang on, this is well established. There's lots of work being done, underneath to make sure all this is, the risks are manageable, etc., etc. Yeah.
That's great. So rather than dominate the conversation, Brandon and Meg, do you want to ask any questions, or do you have any thoughts to share?
Yeah, I guess I had kind of a broad question about scalability of some of not just the systems but the studies, and maybe particularly Little Stringybark Creek, how the kind of not just business models but maybe even ecological benefits seen from something like the activities of green infrastructure establishment in Little Stringybark Creek, how that could be applied to a more urban setting where we're not really looking to get, particularly in LA, we're not really looking to have a huge improvement in the LA River from an ecological standpoint, because we're not really tearing down this trapezoidal channel. There's some restoration efforts, but beyond providing recreation and aesthetics for people, those ecosystem benefits aren't really, we're not really looking to see those in the form of reducing the urban stream syndrome from a hydrological perspective. So I'm wondering if some of those lessons from Little Stringybark Creek, how do you kind of envision those being translated to a more urban setting, even in Melbourne? Thanks.
Yeah, great question, Brandon. In fact, I feel like there's quite a few questions embedded in there in a way, or at least there's a few answers I can see embedded. So the first point, I suppose, is that the benefits in Little Stringybark Creek, our central benefit is a kind of ecological response of the stream. That's what we're pushing for. But in doing so, we see delivery of a substantial water supply. We see quite significant flood mitigation benefits, which we presented at a previous forum, and you were there. And so it may well be that a water authority or waterway management authority wants to address some of those things, wants to address flooding or wants to address water supply, etc., wants to start to improve the aesthetics of a stream without necessarily being able to get much ecological gains, and they could still use the kind of community involvement techniques that we've been using to get those outcomes. So I think in that sense it's very transferable. The other point is that ultimately our real long-term goal is not about restoring this one kind of degraded stream. It's about demonstrating that this LID concept works, and if it's able to restore a degraded stream, it goes, I think, pretty much without saying that it could be used to protect streams that aren't yet degraded and are about to have their catchments developed. And that's really what we're pushing for, that we're trying to develop stormwater management standards and guidelines based on what we've done that say, if you've got a catchment and you're about to develop it, then apply these standards, and that way you can still have urban development, you can still have lovely suburbs to live in, but you don't have to degrade these streams. You can keep these streams so they keep providing all the ecosystem services. If we then think about the long-term trajectory of quite degraded streams, as I say, we might be wanting for those just to reduce flooding or to improve aesthetics or whatever. But I think we should also think about this in a slightly longer term way. All right, each of us probably only lives 100 years or less, but that doesn't mean the world stops when we do. So if we think about, in Melbourne at least, around 2% of a given catchment or area is renovated, rebuilt every year. It's an amazing number, actually. So on average, every surface in a catchment is somehow renovated, rebuilt within 50 years. So it means that if we think about over significant periods of time, we could actually imagine if we put in planning and regulatory requirements that said whenever you rebuild a road, whenever you rebuild a building, you use these stormwater standards that require stormwater retention, etc. You can imagine that over 40, 50 years, you now have a catchment that's got a flow regime and a water quality capable of supporting a healthy stream. Now you're then going to have to go in and do works to fix up that stream, the actual direct physical works. But it's now going to make sense to do it because you will have taken away that kind of catchment impact. Now, to me, sure, it's not going to be something. If we think about some of those, quite degraded inner urban streams, it's not going to be something where I see the benefit in 40 years or 50 years. Well, no, it's not. I'm not going to see it in 10 years, but in 40 or 50 years, there may be the benefit. But I think we need to make a lot of decisions about, let's say, the Earth's future that are over that time frame. When we make cuts in carbon dioxide emissions, same thing, we're not going to see the benefits in 2 or 3 or 5 years. Our aim is really, in my case, my aim is to see that my granddaughter in 60 or 70 years can still live in a world that she's able to live in. So I suppose I see all of those kind of transferable messages. I think there's kind of many of them. But yeah, you're right, we shouldn't get hung up on this is just a project about restoring one degraded urban stream. I think it's much more about processes you could use to fix a whole lot of stream problems, and much more about setting some standards for future development and future redevelopment.
Fantastic, thanks.
I have sort of, I guess, a comment / question that's for everybody. It seemed that sort of listening to all of these talks that we need some kind of framework that incorporates and evaluates risk and uncertainty related to risk across multiple pollutants of concern and multiple kind of end-user goals, whether that's things like storage, harvesting, whatever that may be, so that as we move along, we can incorporate what are now unknown unknowns into some sort of living adaptive model for risk. And I guess what I'm asking is, does anybody know of anybody who's doing this? If so, who and where would we start if it isn't currently being done? I don't know if there are any answers to this question.
My only answer was going to be to say I don't know of such a thing, but I really agree with you. I think again, these are the things that we need to kind of give confidence, not just to those who don't want to pursue these ideas, but we also need those to give confidence to ourselves, because a colleague said to me recently, there might be many things wrong with our current water management system, but their ability to supply us water without making us sick is an incredible achievement that we should not give away lightly, and I think that's a very true statement.
Yeah, well, maybe with that, we'll call the symposium to a close. Thank you so much, Tim, and to the entire panel and set of presenters. This was a really interesting set of presentations. Very, on the one hand, 30,000 foot, so we get the big picture, but then there's a lot of fine scale detail there too, which is really fabulous. It speaks to the high quality of all the research that's being done around the table. So, and thanks, Tim, for sticking it out to the end. You know, ultimately, these course modules are going to be set up so that anybody can click on these talks in any order, and I predict yours is going to be the first that people look at. But anyway, it was really wonderful to hear your perspective in particular, and get your kind of intergenerational long view of what you're doing. I think that's it's inspirational and very sweet. So thank you, Brandon, to sticking it out, and Meg, and we look forward to the next one. So thank you very much, Tim and Brandon.
Yeah, thank you all.
And thank you, James, for putting it together.
Yeah.